Hello, my name is Mason Cipollini with my partners Mackenna and Mayra Mendoza. This is the Sagnac Lab for OPTI 471A. Interferometry is one of the most fundamental concepts in optical sciences. This is a method of utilizing the interference pattern of multiple incident beams to reliably and precisely study a material. Such a concept is important as it allows unparalleled measurement of distance and displacement, surface irregularities, thickness, index of refraction, and deformation, depending on the type of interferometer one may build. Interferometers will typically involve some object, such as a beam splitter or specialized mirror, to split and or recombine the beams of a single source. The Sagnac Interferometer utilizes a common path configuration. An input beam is split by a polarizing beam splitter cube, causing the reflected and transmitted beams to propagate along identical paths through a mirror system before recombining at the cube and into the output. Compared to other interferometers, the Sagnac's construction is highly optimized for rotational measurements with its high photon efficiency, exceptional fringe stability, and resistance to environmental perturbations.
For this lab, we aligned the Sagnac Interferometer using a 632.8 nanometer helium neon laser and polarizing beam splitter cube. We followed the alignment steps from the manual, first guiding the passing beam through the paddles, then adjusting the PVSC for the bent beams, and finally tuning mirrors so that the clockwise and counterclockwise beams overlapped. After placing the analyzer at 45 degrees, we were able to observe interference fringes. Our results matched what was expected. Once the beams overlapped, we saw stable, high contrast fringes, and tapping the table barely affected them. This confirmed the Sagnac's strong common path noise rejection. Rotating the polarizer between 0 to 90 degrees made the fringes disappear and appear exactly as theory predicts. Even though we didn't record the oscilloscope data, we know what the signal should look like. The two photodiodes would show sinusoidal waves that are opposite of each other. When one goes up, one goes down. That's exactly what the Sagnac Interferometer is supposed to do with the phase changes. So even with the oscilloscope, our observations still matched what we expected from the stable and sensitive Sagnac setup.
So what we liked about this lab. Once aligned, the Sagnac's common path stability was great. The fringes barely moved. With the tilted polarizing beam splitter cube, we got complementary outputs and a clean zero-crossing difference signal. Separating the beams let us use the gas cell and two-plate tuner to park phase exactly. What we didn't like, alignment was deceptively difficult. You must close the rectangle so both directions hit the same mirror spots, set the input polarization near 45 degrees into the polarizing beam splitter cube, then overlap at the output with near zero fringe spatial frequency, otherwise the contrast drops. Detector gain/centering is also touchy, and in separated beam mode, the air drafts matter. So how we handled it was we used a strict sequence, aligning the passed arm first, set the bent arm by rotating/shimming the polarizing beam splitter cube close at mirror B so both paths hit the same spot, overlap at the input at analyzer at 45 degrees, and then micro tweaking mirror A and mirror C to land the zero order fringe.